Hi everyone, I'm here to solve numbers 2 and 3 from the Optics for Spectroscopy homework. It's from the Diffraction and Interference section, and the question asks us to solve for the width of a doorway, and it gives us the frequency of the sound that's going through the doorway and the speed of sound, which we all know. So I'm just going to go ahead and solve. First for wavelength, and I'm going to use this equation here. We know that the frequency is 225 hertz and that the speed of sound is 343 meters per second. So I'm just going to do some algebra here. Over 225 equals 1.52, and that's hertz. Now I have, I'm going to use this equation where m equals the number of multiple wavelengths, which we're just going to assume is 1 for the sake of this problem because it doesn't state otherwise. And we're going to also assume that the door is open all the way so that it's at a 90-degree angle so it can let in as much sound as possible. And a sine of 90 degrees is also 1, so I'm going to cancel both those out. And if that's the case, then the width of the door is equal to the wavelength, and we know that the wavelength is 1.52. So I'm going to say that the answer to number 2 is 1.52 meters. And you can also apply this for the second part, or for number 3, which just gives you some different parameters. It tells you that there are 2 minimums. I'm just kind of calling this off the top of my head. I don't have the problem in front of me. And that the angle is 19.5 degrees, and then that the width of the opening is 3 micrometers, or micrometers, however you say that. So I'm just going to set up the problem and solve. I'm going to convert that into meters. And then we have sine 19.5 degrees equals 2 wavelengths. And that ends up equaling 501 nanometers, or 5.01 times 10 to the negative 7 meters, equals the wavelength of that wave that would go through that opening.